Welcome, curious minds, to the deep dive. Today we're setting out on what I think will be a truly monumental journey. We're heading not just across our solar system, but right to its outermost, most mysterious frontiers. Imagine standing at the very edge of our cosmic neighborhood, so incredibly far out that our magnificent sun, the giver of all life, is just another bright star in the cosmic tapestry. A point of light no more dominant than thousands of others. What lies out there in that profound darkness? What secrets might it hold about, our cosmic origins and maybe even our future? Today, we're setting our sights on a theoretical, unseen sphere of icy objects known as the Oort Cloud. You sent us a really fascinating stack of articles, research notes, all sorts of stuff about this enigmatic region, and our mission today is to extract the most important nuggets of knowledge and insight from them. It's a place so vast, so diffuse, it almost defies imagination, a kind of cosmic deep freeze that represents the true cosmographic edge of the sun's gravitational domain. Okay, let's unpack this. The Oort Cloud, it sounds like something straight out of a sci-fi novel, doesn't it?
A true cosmic frontier that's both fundamental to our understanding and, frankly, utterly mysterious.
You've absolutely touched on something truly fascinating there. The Oort Cloud is indeed one of the most intriguing yet least understood parts of our solar system. And you're right, its existence is primarily a scientific hypothesis. It's inferred, really, from the behavior of long-period comets, which makes it a powerful example of how we see the unseen through careful observation and mathematical modeling. So throughout this deep dive, we'll get into its colossal scale, how it gives us these crucial clues about the formation of our solar system. We'll consider if, maybe all stars boast such structures. We'll discuss its role as the source of our most dramatic comets, explore the, really compelling evidence for a planet potentially hiding within it, and finally, look at its truly speculative uses for, future interstellar ventures. It's a realm that constantly challenges our perceptions of what lies beyond.
Okay, so before we dive into all those secrets, where exactly is this Oort Cloud, and how do we even begin to grasp its sheer mind-boggling size? Because honestly, the numbers involved are just astronomical. They're incredibly difficult to visualize.
You're completely right. The scale is genuinely difficult to convey. Let's start with a clear definition, though. The Oort Cloud is a theoretical, vast spherical shell. We think it contains billions, maybe even trillions, of icy objects that orbit our sun way, way out. It was first postulated, as you probably know from the sources, by the Dutch astronomer Jan Oort back in 1950. He based it on his meticulous observations of long-period comets. He needed a scientific explanation, right, for where these new comets, arriving seemingly from all directions, were continuously originating, and that led him to hypothesize this distant spherical reservoir. Now, what makes these objects so profoundly valuable for science is their composition. They're primarily made of what we call volatile ices, and that's not just water ice, which we often think of first, but also things like methane, ethane, carbon monoxide, even more exotic stuff like hydrogen cyanide and ammonia. You can imagine these as the fundamental frozen ingredients of a planetary system, all mixed in with tiny grains of silicate dust, and surprisingly, some pretty complex organic molecules. What's truly extraordinary is that these are essentially pristine, deep frozen samples of the primordial solar nebula. They've been preserved almost unchanged since the very birth of our solar system, about 4.6 billion years ago. They are, in the truest sense, time capsules.
Wow, actual time capsules from the beginning. So the scale, use it as vast. Help us picture that.
Okay, scale. The Oort Cloud isn't just far away. It literally defines the very boundary of the sun's gravitational influence. It stretches from approximately 2,000 astronomical units, or AU, at its inner edge.
And an AU is the Earth-Sun distance, right? About 93 million miles.
Exactly. So it starts at 2,000 AU and goes all the way out to 100,000 AU, and some estimates even push it to 200,000 AU at its outermost boundary. To put that in perspective, Neptune, our farthest known planet, is only about 30 AU from the sun. So the Oort Cloud begins thousands of times further out than Neptune.
Thousands of times.
Yeah. Imagine this, if the entire solar system, all the way out to Neptune, was compressed into the space of a single football field. The Oort Cloud wouldn't just be beyond the stadium walls. It would stretch for hundreds, maybe thousands of football fields beyond that, fading out into this immense diffuse sphere. That's the staggering scale we're talking about. It marks the true edge of our solar system's gravitational domain.
That's just mind-boggling. To help us further wrap our heads around those numbers, which are truly vast, how long would it take for, say, light or even our fastest spacecraft to get there? Because even at millions of miles an hour, it still sounds like a multi-generational trip.
It absolutely is. It's a trip that really defies human timescales. Let's use time as our ruler, like you suggested, because it makes these unimaginable distances a bit more, well, relatable. Light from the sun takes a little over 8 minutes to reach Earth,
No?
and about 4.5 hours to reach Neptune's orbit.
Okay, 4.5 hours in Neptune.
Right. Now, just under 3 hours after passing Neptune's orbit, sunlight passes beyond the outer edge of the Kuiper Belt. That's our sort of inner icy ring. However, it will take another 10 to 28 days for that same sunlight just to reach the inner edge of the Oort Cloud.
Days, just to the start of it.
Days, and to traverse the entire Oort Cloud from its inner boundary to its outer edge. Sunlight could take as long as a year and a half.
A year and a half at the speed of light.
Precisely. That's the amount of time light, the fastest thing in the universe takes. Now consider our fastest spacecraft, NASA's Voyager 1. It's currently the farthest human-made object from Earth, right? About 163 AU from the sun and traveling at roughly 17 kilometers per second. That's about 1 million miles per day, or, 0.006% of the speed of light. Pretty fast, but...
Still slow compared to light, yeah.
Exactly. Even at that incredible speed, Voyager 1 won't even enter the inner edge of the Oort Cloud for another 300 years.
300 years.
And to pass through its entire expanse to finally exit the outer edge, it would take an estimated 30,000 years.
30,000 years.
Wow, imagine setting off on that journey. It would have to be a multi-generational mission, wouldn't it? The crew that arrives wouldn't even be the crew that left. We'd need to invent suspended animation or truly embrace a slower, more deliberate form of exploration. That really highlights the immense, almost incomprehensible distances involved. It pushes the boundaries of human endurance and technology.
Wow, 30,000 years. That really puts it into perspective. So it's not just big, it's essentially invisible and incredibly diffuse to us, right? We've never actually seen the Oort cloud itself, have we? Despite its fundamental importance.
That's absolutely correct. The Oort cloud has never been directly observed. And this is precisely due to its extreme distance and its, well, incredibly low density, although we think it contains, 10 to the power of 12, maybe 10 to the power of 13 icy objects, a huge number with a total mass equivalent to about 100 Earths. The sheer volume it occupies is so immense that it is, for all practical purposes, empty space.
So even with trillions of objects, it's still mostly empty.
Exactly. The average distance between individual comets in our own Oort cloud is estimated to be tens of millions of kilometers. Imagine that kind of separation. It's like scattering, a handful of grains of sand across an entire continent. And this extreme sparseness means the cloud is transparent, doesn't block a meaningful amount of light from our sun. For comparison, think about nebulae. We can see them because of what's called the fog wall effect, right? Millions of particles are close enough together to refract and diffuse light. The Oort cloud simply isn't dense enough for that to happen. The individual objects are just too small and too far apart to reflect enough light for us to see them directly, especially across interstellar distances. Even our most powerful telescopes, like Hubble or James Webb, they can observe objects smaller than, say, 300 kilometers in diameter at a distance of 0.3 light years, which is roughly 62,000 AU. That's well within the Oort cloud's range. So direct observation of typical Oort cloud objects, practically impossible with current tech. And just to illustrate further, the faintest exoplanetary debris disks that our most advanced instruments like LMA can detect, they're estimated to be at least 1 million times denser than a hypothetical Oort cloud would be.
1 million times denser.
Wow. Yeah. So what's really fascinating here is that we know the Oort cloud is there, not by seeing it directly, but by inferring its presence, like you said, from the behavior of those long-period comets. It reminds me of how ancient mariners hypothesized lands beyond the ocean just by observing unique driftwood that, could only come from a distant, unknown source. It's a profound testament to scientific deduction and the power of indirect evidence. It paints a picture of a cosmic structure that is as real as it is elusive.
So we've established the Oort cloud is unimaginably vast, incredibly distant, and largely invisible. It's truly a ghost of our solar system. But that just begs the question, how did this diffuse, icy graveyard of cosmic material even come to be in the first place? What ancient chaotic events sculpted our solar system's outermost frontier? What does the Oort cloud tell us about the formation and the chaotic early history of our solar system?
Right. The Oort cloud is, in essence, a relic of our solar system's violent youth. Astronomers theorize that the objects we find in the Oort cloud today, they didn't actually form out there in the frigid depths. Instead, they probably formed much closer to the sun, specifically in the colder outer regions around the present-day orbits of Uranus and Neptune. Then, during the early, turbulent stages of our solar system's formation, when the giant planets were still settling into their orbits, these icy planetesimals were then gravitationally kicked or scattered or maybe pushed out to their current distant position.
Kicked out by the planet.
By the giant planets, yes. This was a consequence of powerful gravitational interactions with the massive young giants, Jupiter, Saturn, Uranus, and Neptune. They acted like a colossal cosmic slingshot. This ejection event is actually a key component of modern solar system formation models, like the NICE model. Have you come across that in the sources?
Nice model, yeah. Named after the city, right? It talks
Yeah.
about planets migrating.
Exactly. The NICE model describes a period of dynamic instability among the giant planets, likely occurring maybe 500 to 700 million years after the Sun formed. During this period, the orbits of Jupiter, Saturn, Uranus, and Neptune migrated significantly, and this caused widespread gravitational disruptions that scattered vast numbers of these icy planetesimals. Some were thrown inwards, potentially triggering events like the late heavy bombardment on the inner planets.
Okay, so that's linked.
It's thought to be linked, yes. But many more were flung outwards, forming the Oort Cloud and also the scattered disk of the Kuiper Belt. It paints a picture of a far more dynamic and chaotic early solar system than we once imagined. It wasn't neat and orderly at all. And this violent scattering also explains the Oort Cloud's unique spherical shape. Unlike the Kuiper Belt, whose objects largely formed in situ, where they are now, and mostly remain in a flattened disk aligned with the ecliptic plane.
The same flat plane the planets orbit in.
Right. The Oort Cloud's objects were scattered isotropically. That means in virtually all directions. This random scattering created its encompassing spherical shell, and as you go further out, the Oort Cloud structure is significantly shaped not just by our sun, but by external gravitational forces too. In the inner Oort cloud, say from about 50 to 2000 AU, objects are still somewhat affected by our planet's gravity, but between 2000 and 15,000 AU, the main influence becomes galactic tidal forces, the differential gravitational pull of the Milky Way galaxy itself.
The whole galaxy is pulling on it.
Wow, yeah, subtly stretching and shaping it. And even further out, in the outer Oort cloud, from 15,000 to maybe 100,000 AU, objects are heavily affected by the gravity of other stars passing nearby. These flybys can easily perturb their orbits. Beyond this point, the sun's gravity just isn't strong enough to keep objects bound.
So it's not just our sun's history, but the entire galaxy that's pulling the strings out there, subtly stretching and shaping this distant realm. I also saw something about our Oort cloud potentially forming a spiral structure. That sounds quite beautiful and, well, surprising for such a diffuse region.
It is indeed a surprising finding, and it's the result of very recent research, actually. New simulations using NASA's Pleiades supercomputer have proposed that the inner Oort cloud forms a kind of spiral structure. This spiral stretches about 15,000 AU in length and is oriented nearly perpendicular to the galactic plane. And this phenomenon is a direct result of those very galactic tidal forces we just mentioned.
So the galaxy's pull creates a spiral. How does that work?
Well, imagine our entire galaxy as this immense, slowly swirling gravitational current. This current doesn't pull equally on all parts of the Oort cloud. It subtly stretches and deforms it, much like the moon's gravity creates tides on Earth, but on a truly cosmic scale. This slight variation in gravitational pull across such vast distances plays a profound role in shaping this region, especially because bodies in the inner Oort cloud typically evolve very slowly, and many are often ejected by planets before they can ever heat up and become active comets. This specific region's unique spiral shape gives researchers a new avenue to study its evolution and understand the subtle forces at play.
Okay, now here's where it gets really interesting for me. Some sources suggest our Oort cloud might not be entirely ours. The idea of our Oort cloud being a composite library of stellar history filled with material from other stars. That's genuinely mind-bending. It fundamentally shifts our perspective, doesn't it? Our solar system isn't just this secluded island, but maybe it was a vibrant intergalactic exchange point right from its very beginning. What does this tell us about, the commonality of life's building blocks, or even about the potential for life to seed across stellar nurseries? Could it contain material from other stars, making it a truly cosmic melting pot?
Your observation is absolutely spot on, and the evidence strongly points to that possibility, making the Oort cloud even more profoundly fascinating. The Sun, like most stars, is believed to have formed within a stellar cluster, a dense stellar nursery, with hundreds or even thousands of sibling stars. So imagine our sun not being born in isolation, but in this crowded, bustling cosmic neighborhood. During this early crowded phase, the nascent Oort clouds of these neighboring stars could have overlapped significantly.
So they were all mixed together.
Yeah, potentially. Gravitational interactions within the cluster would have made it entirely possible for stars to steal comets from one another's protoplanetary disks and for our sun to capture free-floating debris, essentially borrowing ingredients from other forming star systems. Some models even suggest that a significant fraction, potentially even the majority of the objects in our Oort cloud, may have originated around other stars and were then captured by the sun before the birth cluster dispersed and those stellar siblings drifted apart.
The majority.
Yeah. Some research estimates that about half the inner Oort cloud and maybe a quarter of the outer Oort cloud could be non-native to our solar system. This hypothesis implies that the Oort cloud is indeed a composite library containing not only the story of our own solar system's formation, but also chapters from the histories of its long-lost stellar siblings. It's like finding books from other galaxies on your shelf, right? Offering direct insight into the chemical makeup and conditions of other nascent stellar systems. And it certainly raises intriguing questions about the distribution of complex organic molecules, the building blocks of life across these early stellar nurseries.
That's incredible. So not just our history, but pieces of other star systems history too.
Exactly. And that's not all that challenges our assumptions about the Oort cloud. It isn't just composed of homogeneous icy objects. We've had some surprising discoveries, like an object called C2014 S3, Pan-STARRS. It was nicknamed a Manx comet after the tailless cat breed.
A tailless comet.
Because this object travels on an orbit typical of a long-period Oort cloud comet, yet it exhibits the spectral characteristics of a rocky S-type asteroid, and it displays very little or no cometary activity, hence the tailless moniker. It's thought to be a piece of fresh inner solar system Earth-forming material, essentially, a chunk of rock that might have otherwise become part of a terrestrial planet like Earth that was ejected billions of years ago and then preserved in the deep freeze of the Oort cloud.
So a piece of the inner solar system thrown way out there.
Precisely. This discovery offers a direct link between the innermost and outermost regions of the primordial solar system. It shows that rocky material from the inner solar system can be preserved in the Oort cloud for eons. Theoretical models suggest that maybe 1–2% of the Oort cloud's population could consist of such rocky material that formed much closer to the sun. Which raises an important question, doesn't it? If we found material from the inner solar system preserved out there, and even material from other stars, what else might be hiding in this cosmic attic, awaiting discovery? It really makes you wonder what other secrets might have been preserved in this cosmic deep freeze.
It really does. Okay, let's talk about comets more directly. With their spectacular tails, they're often our first most visible encounter with these distant regions, even if it's indirect. So it's a critical question. Do all of our comets really come from the Oort cloud?
That's a great question, and the straightforward answer is no, not all of them. We actually have two main populations of comets, and they each originate from a different, though still distant, region of our outer solar system. Each tells a slightly different story about our cosmic past. First, we have the short-period comets. These are defined as comets that complete an orbit around the sun in less than 200 years. Their orbital characteristics are quite distinct. They almost all orbit the sun in the same direction as the planets, that's prograde motion, and they have low inclinations, meaning their paths lie close to that flat ecliptic plane.
Okay, short period, less than 200 years, orbit like the planets. Where do they come from?
They primarily originate from the Kuiper Belt. The Kuiper Belt is that vast, sort of torus-shaped junkyard of icy bodies left over from the solar system's formation, located just beyond Neptune's orbit, extending from about 30 to 55 AU. Unlike the scattered objects of the Oort cloud, Kuiper Belt objects, or KBOs, largely formed right where they are today. The short-period comets are specifically sourced from a region of the Kuiper Belt known as the scattered disk, where objects have more eccentric orbits. These bodies are occasionally perturbed by gravitational interactions with Neptune, which can nudge them onto paths that bring them into the inner solar system. Halley's Comet is probably the most famous short-period comet, although it has a somewhat unusual retrograde orbit, but it's generally representative of this group.
Got it. Kuiper Belt for the short period ones. So the Oort cloud is for
the long-period comets. These are the ones primarily thought to originate in the Oort cloud. They are characterized by taking more than 200 years to orbit the sun, often thousands or even millions of years. And unlike their short-period counterparts, long-period comets tend to have randomly oriented orbits, not necessarily anywhere near the ecliptic plane. Their paths are highly eccentric, meaning they stretch far, far out from the sun, sometimes plunging almost directly towards it before swinging back out into the deep beyond. This isotropic or all-directional distribution is a key indicator of their Oort cloud origin. Comet Hale-Bopp, which was so visible back in 1997, is a prime example of a spectacularly bright long-period comet.
Right, I remember Hale-Bopp. So the Oort cloud explains these long-period visitors coming from all directions.
Exactly. For thousands of years, astronomers observed comets approaching Earth, lighting up the night sky with their, erratic appearances, then often quickly disintegrating as they made their fiery approaches to the sun. This consistent yet seemingly random arrival pattern of fresh comets that had never been near the sun before, led to the strong conviction that there must be a fresh supply. The idea was that there had to be a cold, distant region that could continuously replenish the supply, a vast reservoir that had remained largely untouched since the solar system's birth. The Oort cloud fits this role perfectly.
And the comet activity, the tails and stuff, that's the ice turning to gas.
Precisely. Comets become active and form their characteristic coma, that's the hazy envelope around the nucleus, and their spectacular tails as they approach the sun because their volatile ices like water, methane, ammonia sublimate. That means they turn directly from solid to gas due to solar radiation. This process releases dust and gas, creating the brilliant display we see. And it's not just the ice-rich comets that show activity. Even those Manx comets we discussed, the rocky ones on Oort cloud orbits, they still display a very faint, weak level of comet-like activity.
Even the rocky ones.
Yeah, it's 5 to 6 orders of magnitude less active than typical ice-rich comets, but it's still believed to be produced by the sublimation of a tiny residual fraction of volatile ice that they've somehow managed to retain. It just demonstrates the extreme deep freeze conditions out there in the Oort cloud. So if we connect this to the bigger picture, comets are essentially dynamic time capsules. They're not just beautiful celestial displays, they're icy messengers carrying pristine material that has remained largely unchanged since the early solar system. They offer direct clues to its original composition, temperature, and the processes that shaped it. By studying them, we learn about the distant, invisible Oort cloud itself.
It's fascinating how our solar system's story involves this dynamic and beautiful frontier, and that leads me to wonder about its cosmic neighbors. If our sun, like many stars, formed in a cluster and perhaps even exchanged material for its Oort cloud, does that mean most, or even all, stars out there likely possess similar icy structures? Or is our Oort cloud somehow special?
That's a truly profound question, one that moves us beyond our immediate solar neighborhood and into the broader galactic context. While we have very little direct observational evidence, theoretically, astronomers believe Oort clouds should be quite common throughout the galaxy. It's not crazy to think, as some of the sources put it, that smaller stars might have smaller Oort clouds and larger stars, larger ones, proportionally. The raw materials for building these structures, vast populations of icy planetesimals, are considered common byproducts of star and planet formation. Wherever stars form, especially with planetary systems, there's a strong likelihood of these icy reservoirs being created through gravitational scattering.
Okay, so the ingredients are common.
Right. And furthermore, that theory we discussed, that a significant portion, maybe even the majority, of the comets in our own Oort cloud originated from other stars' protoplanetary disks and were then captured by our sun, that strongly implies that Oort clouds are not unique to our sun. This interstellar exchange suggests they are a common feature of stellar systems, forming, interacting, and evolving within their crowded birth environments.
Okay, if they're common, why haven't we definitively seen them around other stars with our powerful telescopes like James Webb? It feels like if they're out there, we should be able to spot them, given all the exoplanets we're finding now.
That's precisely where the immense challenges of detection come in. The extreme low density of objects in an Oort cloud makes them virtually invisible across interstellar distances. To illustrate again, our own Oort cloud contains about 10 Earth masses spread over a volume that's 10 to the power of 20 times greater than Earth's volume.
That number is just huge.
It makes it, for all intents and purposes, essentially empty space. The individual icy bodies are simply too small and too far apart, not only from each other but also from their host star, to reflect enough light for us to see them directly across the vast distances separating star systems. It's like trying to spot individual snowflakes in a blizzard happening hundreds of miles away, even if there are trillions of them. They're too small and too spread out to form a discernible mass.
So it's not like a nebula, which we can see.
Exactly. We can see nebulae because light is refracted and diffused by millions of particles relatively close together. The Oort cloud is far too sparse for that. The only attempt so far to directly detect Oort clouds around other stars involved looking for excess low-temperature emission using cosmic microwave background observations. Basically, trying to detect the faint thermal glow of trillions of extremely cold bodies. But unfortunately, there have been no definite detections. Our current observational technology is limited to seeing only the innermost, most concentrated tip of the iceberg of extrasolar debris. These are typically dense, flatter planetesimal belts or exocomet belts that are analogous to our Kuiper belt, residing much closer to their host stars. The exceptionally faint and diffuse Oort cloud structure itself remains beyond our grasp with current technology.
Oh, okay, so we see the Kuiper belt equivalents, but not the Oort clouds themselves.
That's a good way to put it. Despite the challenges of directly observing Oort clouds, we do have compelling evidence for their denser cousins, these exocomet belts. Surveys using instruments like ALMA have revealed, I think the count is 74 such debris disks surrounding planetary systems close to our own. Stars like Vega and Beta Pictoris, for instance, are known to have significant debris disks teeming with icy bodies. These exocomet belts are visible using submillimeter radio telescopes, which are sensitive to millimeter-sized particles. These particles are generated by collisions between Kuiper belt-like objects and, in warmer belts, possibly by the sublimation of surface ices. These belts have been found to be not only larger than previously thought, but also extend more widely, often resembling a donut with a small hole rather than a narrow onion ring. While these discoveries confirm that the raw materials for building Oort clouds are common throughout the galaxy, they still don't provide direct evidence for the existence of the final, scattered, and exceptionally faint Oort cloud structure itself.
Okay, that makes sense. But you mentioned our sun potentially stealing comets from other stars in its early days. Does that mean our Oort cloud could actually interact with the Oort clouds of other stars today, even if they're so far apart? It still sounds like an incredibly rare event.
It's an excellent point, and while it is relatively rare on human timescales, it absolutely can happen, which again points to the dynamic nature of these regions. Stars pass within 1 light-year of our sun relatively infrequently. The ballpark figure is maybe every million to couple million years or so. But when they do, their gravitational influence can significantly perturb our Oort cloud, sending ripples through its vast expanse. The last confirmed close passage was Schultz's star. It's a small binary system, an M9.5 star and a brown dwarf, with a combined mass about 15% that of the Sun, and it passed by about 70,000 years ago.
70,000 years ago. That's like yesterday, cosmically speaking.
Pretty much. This star passed within approximately 0.82 light-years, which is about 50,000 AU, moving directly through our Oort cloud. It's unclear if our inner solar system passed through its Oort cloud, or if our sun stole material from it, but the gravitational interaction was certainly significant. It potentially stirred up our icy depths.
So could that encounter send comets our way?
Well, if Schultz's star did redirect some of our Oort cloud comets towards Earth, it would take an estimated 2 million years for them to actually reach the inner solar system. So we might start seeing some of those comets disturbed by that ancient flyby in about 1.93 million years from now.
Okay, so not tomorrow then.
Not tomorrow, no. But looking to the future, another larger star, Gliese 710, about 60% the mass of the Sun, is predicted to pass within 1 light-year of Earth in approximately 1.36 million years. This future encounter could cause further perturbations, potentially sending another wave of long-period comets our way. These close encounters with passing stars can gravitationally perturb objects in the outer Oort cloud, sending them hurtling towards the inner solar system as long-period comets, or even ejecting them from the solar system entirely. It confirms that the Oort cloud isn't just a static, distant boundary. It's a dynamic, porous region influenced by our galactic neighborhood. It's constantly exchanging and redirecting material, acting as a kind of cosmic buffer zone for our solar system. It reminds us that even in the vastness, we're not entirely isolated, and our deep past and distant future are constantly being subtly shaped by our stellar neighbors.
Okay, this is definitely where it gets really interesting, and I think it speaks to that inherent human curiosity about what's just beyond our sight. We've talked about comets and icy bodies, but could there actually be something much bigger, a planet lurking in the Oort cloud, on a very long elliptical orbit, completely undetected? And what exactly makes this evidence so compelling that it's got the scientific community buzzing, especially after decades of Planet X theories that kind of fizzled out? What's different this time?
That's an excellent and critical question because you're right. The idea of an unknown planet beyond Neptune, sometimes called Planet X, has a long and storied history. It dates back to Percival Lowell's search in the early 20th century, which famously led to Pluto's discovery in 1930. However, Pluto was soon determined to be far too small to be Lowell's predicted Planet X, which was hypothesized back then to explain supposed wobbles in Neptune and Uranus's orbits. For decades, the case for a large unseen planet seemed to close, especially after Voyager 2 data in 1989 showed no remaining orbital discrepancies in Uranus or Neptune's movements.
So the original reason for Planet X went away.
Exactly. This time, the evidence is different. It comes from the clustering of much more distant, smaller objects, not from the orbits of the known giant planets. The conversation dramatically reopened in 2016. Caltech researchers Konstantin Batygin and Mike Brown, building on earlier work by Chad Trujillo and Scott Shepard, presented strong mathematical modeling and computer simulations suggesting solid evidence for a real ninth planet. They've dubbed this hypothetical object Planet 9, though crucially, it hasn't yet been directly observed. Mike Brown himself has stated, quite compellingly I think, there have only been 2 true planets discovered since ancient times, Uranus and Neptune, discounting Pluto, and this would be a third. It's a pretty substantial chunk of our solar system that's still out there to be found, which is pretty exciting.
So what is this new evidence? What are they seeing?
The evidence for Planet 9 comes from the peculiar and statistically improbable clustering of the orbits of a specific group of distant trans-Neptunian objects, or TNOs. These are sometimes called sednoids, after the dwarf planet Sedna, discovered in 2004, and another object, 2012 VP113, discovered in 2014. These objects have unusually high perihelion distances, that's their closest approach to the Sun, distances too large to be explained by gravitational interactions with known planets like Neptune. Chad Trujillo and Scott Shepard were the first to note that 13 of the most distant Kuiper Belt objects shared similarities in an obscure orbital feature.
Okay, so a few distant objects look weird.
Right, but Batygin and Brown refined this. They found that the orbits of 6 extreme TNOs, those with semi-major axes greater than 250 AU, meaning their average distance from the Sun is at least 250 times Earth's distance, and perihelia beyond 30 AU were strikingly aligned in space. Their perihelia, the points of closest approach to the Sun, were clustered in roughly the same direction. And their orbital planes were also tilted similarly, leading to a clustering of their longitudes of ascending nodes. This isn't just a random pattern, it's like a gravitational signature.
Aligned orbits. How unlikely is that?
The likelihood of this combination of alignments happening by pure chance is astonishingly low, only 0.007%. And importantly, these clear objects were discovered by 6 different surveys on 6 different telescopes, which makes it far less likely that this clumping is just due to some observational bias, like looking in one particular patch of sky. Furthermore, this observed clustering shouldn't persist over billions of years due to a process called precession, where orbits slowly rotate over time. This effect should smear out such alignments. The fact that this clustering does exist indicates that it is most likely maintained by the gravitational field of an as-yet undiscovered massive object orbiting the Sun. It's like this unseen planet is locking these TNOs into their unusual synchronized paths. It's a powerful indirect gravitational signature, a cosmic dance choreographed by an unseen partner.
Wow. Okay, so based on that gravitational choreography, what do they think Planet 9 is like?
Based on this orbital clustering, Planet 9 is estimated to have a mass between 5 and 15 Earth masses. This would make it a super-Earth or mini-Neptune type planet, a class of planet that is incredibly common in exoplanet systems we're finding elsewhere, but has been conspicuously absent in our own solar system until now, maybe. Its orbit is predicted to be highly elliptical, with a semi-major axis, or average distance from the Sun, somewhere between 400 and 800 AU. And it would take a staggering 10,000 to 20,000 Earth years to complete just one orbit around the Sun.
10 to 20,000 years. And you said this makes our solar system more normal.
Intriguingly, yes. The existence of such a planet would actually make our solar system more normal compared to the thousands of exoplanet systems astronomers are finding around other stars. Most exoplanet systems feature planets with masses between Earth and Neptune, which is the most common type of planet found elsewhere, and many exoplanets also follow exceptionally distant or wide-ranging orbits. So our solar system might not be as unique or, deficient in this type of planet as we once thought.
So, if it truly exists, how would a planet as massive as 515 Earths end up in such a bizarre, distant orbit, way out there in the Oort Cloud-like region? It's certainly not where we typically expect a planet to form and remain.
That's a critical part of the hypothesis, absolutely. And there are several plausible scenarios, all of which speak to that dynamic and often violent early history of our solar system. One leading theory suggests Planet 9 formed closer to the Sun, much like the other giant planets. But then, during that period of dynamic instability among the young giant planets, that turbulent early solar system we discussed with the NICE model, it was gravitationally kicked out into its highly eccentric, distant orbit.
Kicked out like the Oort Cloud objects.
Similar process, yeah. In this scenario, its growth would have been halted early by the ejection, leaving it less massive than Uranus or Neptune. It's like a child being expelled from the family home into a distant, lonely exile. Another fascinating possibility is that Planet 9 formed in another stellar system entirely and was later captured by our sun's gravity during a close encounter between stars in the sun's birth cluster. Imagine our sun as a young star passing by a sibling star that had already formed its own planets, and through a delicate gravitational dance, it snatched one of its planets.
Stolen planets. That fits with the stolen comets idea.
It does, doesn't it? While perhaps less likely, it could also have been a free-floating or rogue planet wandering through interstellar space that was subsequently captured by the sun's gravity. A more recent model proposes that dynamical friction from a massive belt of planetesimals estimated at 130 Earth masses in the outer parts of the protoplanetary disk could have allowed Planet 9 to be captured into a stable, eccentric orbit, effectively slowing it down enough to stay bound. These various scenarios highlight the dynamic, sometimes violent, early history of planetary systems, where planets can be exchanged between stars or exiled to the fringes of their home system. It truly speaks to the chaos of planetary formation.
So are planets like this expected to be common out there?
Well, beyond the specific hypothesis of Planet 9, simulations suggest that such Oort cloud planets could actually be a common phenomenon throughout the galaxy. Between 2% and 10% of stars that undergo giant planet instability, a process believed to occur in many systems could end up with a planet trapped in their Oort cloud. Given that perhaps 75–90% of giant planet systems must go unstable to match the observed exoplanet distributions, and with over 100 billion stars in our galaxy, well, you do the math. There could be tens to hundreds of millions of planets lurking in the Oort clouds of other stars.
Hundreds of millions. Wow.
Yeah. And furthermore, any system with a few gas giants is likely to have many smaller bodies, asteroids, comets, rocky planets, even large moons that could also be tossed into the Oort cloud during such seismic events. The Oort cloud, then, might not just be an icy graveyard, but a hidden refuge for countless exiled worlds.
So the search is ongoing.
Absolutely. The search for Planet 9 continues, with astronomers like Mike Brown actively encouraging other researchers to get inspired and start searching, providing a kind of treasure map of its likely location based on the TNO alignments. Telescopes like the Subaru telescope in Hawaii with its wide field of view are actively involved, sifting through vast amounts of data. Finding Planet 9 wouldn't just be about completing our solar system's planetary census, it would also offer invaluable insights into the formation and evolution of giant planets, not just in our own solar system, but also shedding light on the thousands of giant exoplanets observed around distant stars. This isn't just about finding a new planet, it's about understanding a missing piece of our solar system's puzzle, fundamentally reshaping our understanding of how planetary systems are built and evolve, and how common oddball planets actually are.
Okay, from its ancient origins and connection to our solar system's tumultuous birth, to potentially harboring a hidden planet that defies our current understanding. The Oort cloud is clearly a place of immense scientific interest. But looking much further into the future on timescales of centuries or even millennia, what else could this distant, icy realm be used for by humanity? Could it be more than just a scientific curiosity?
That's a fascinating question, moving into the realm of, well, science fiction almost, but grounded in potential reality. The Oort cloud, despite its current inaccessibility, holds incredible, albeit highly speculative, potential for humanity's far future. First, let's consider it as a vast repository of resources. Its trillions of comets represent an enormous storehouse of valuable volatiles. These bodies are incredibly rich in water, methane, ammonia, other carbon and nitrogen compounds, all essential for life support systems, for future space habitats, and for manufacturing propellants for spacecraft. They also contain silicate dust with ferrous metals, offering raw materials for construction.
Mining the Oort cloud. That sounds ambitious.
Extremely ambitious. Far future concepts envision colossal, fully autonomous mining superstructures, perhaps powered by advanced fusion reactors that could synthesize their own fuel from the very matter they collect. These massive operations could navigate the cloud, identify resource-rich comets, and process their materials in situ, maybe sending processed goods back to an inner solar system that might have exhausted its more easily accessible resources centuries from now. While certainly not an economically viable proposition for the foreseeable future, it stands as a fascinating thought experiment for a truly spacefaring Type 2 civilization, one capable of harnessing its entire stellar system's energy output.
Okay, mining is one thing. What about living there? Some sources mentioned a cometary civilization.
Right. Building upon the idea of resource extraction, physicists like Freeman Dyson and others have explored the concept of a cometary civilization. This is a highly speculative but captivating vision where humanity, or perhaps its descendants, could permanently expand into the Oort Cloud itself. Imagine these habitats not just as simple cylinders, but as entirely self-sustaining microworlds, perhaps miles long, slowly migrating through the void, each a self-contained ecosystem. What kind of society would emerge in such an environment? Small, nomadic groups, maybe communities of about 25 to 50 people, could inhabit these O'Neill-style cylinders, constructed directly from these abundant cometary materials. With larger clusters of maybe 500 individuals occasionally coming together for social and genetic diversity, these would be societies deeply adapted to the profound cold and silence of interstellar space.
Living in total darkness and cold. How would they get power?
That's a monumental challenge. Energy generation in this deep freeze environment would be critical. Solar power, impractical. It becomes infeasible past the inner solar system's asteroid belt. Instead, energy would need to be generated either through compact fusion reactors using deuterium extracted from cometary ice, or perhaps by harnessing the faint light of distant stars with vast mirror farms thousands of kilometers across, meticulously angled to capture every photon. Nuclear fission is also seen as a primary reliable choice for deep space power. Communication would be another profound challenge. With communities separated by light weeks or even light months, real-time conversation would be impossible. Perhaps a culture of asynchronous messaging would emerge, vast data packets ferried by robotic probes, where conversations span generations, forcing a new kind of patience and long-term thinking. These wouldn't just be outposts. They could be new, evolving expressions of humanity, redefining everything from economy to family structure, utterly adapted to life in the profound darkness between the stars.
Talk about extreme social distancing. But for a species with an insatiable drive to explore and adapt, this sounds like the ultimate frontier, a new definition of home in the cosmos, pushing the very boundaries of what it means to be human.
It absolutely does. And the Oort Cloud could serve an even grander purpose, as a way station for interstellar travel. It could be a proving ground for even deeper space technologies aimed at crossing the gulf between the stars, acting as permanent settlements or way stations offering resources for truly millennial journeys. Interstellar space, we're discovering, isn't completely empty. It contains trillions of icy bodies, including Oort Cloud objects and possibly even rogue planets. A hypothetical method of slow, crude interstellar travel involves island hopping, moving from body to body across the Oort Cloud and beyond, exploiting these resources as fuel and materials to build ever larger multi-generational spacecraft.
Island hopping between comets.
Yeah, it contrasts with the idea of fast crewed missions, which would require enormous energy, huge generation ships, or suspended animation, or just sending tiny, uncrewed probes that merely observe. The Oort Cloud could be our first stepping stone out of our solar system, our cosmic dockyard, so to speak.
But the challenges must be immense. Just getting there, let alone living there or using it as a base.
Oh, absolutely. Any future endeavors in the Oort Cloud face formidable challenges. Just sending probes requires long-duration missions, immense fuel, highly redundant communication systems, and instruments designed to last for half a century or more in extreme cold and radiation. For example, one concept involves a nuclear-propelled probe that could rendezvous with an incoming Oort Cloud object and effectively act as a distant observatory stationed tens of billions of miles beyond Pluto for decades. But that would necessitate a massive upgrade of our deep space network infrastructure on Earth, the Moon, and in space, just to handle communication over such incredible distances and time lags.
And what about faster-than-light travel? Even if we figure that out, would the Oort Cloud be a hazard?
That's another truly speculative challenge. Even if hypothetical FTL concepts like the Alcubierre warp drive were possible, which aims to bend space-time around a vessel, the extremely low-density particles and objects in the Oort Cloud could still pose catastrophic collision risks at such immense speeds.
Even single atoms.
Potentially, yes. While individual objects are incredibly far apart, tens of millions of miles, even the few atoms occupying every cubic meter of space can become a serious problem at near-light speeds, let alone FTL, which would amplify impacts to catastrophic levels. However, for perspective, the Oort Cloud is actually more empty than the asteroid belt, where average distances between objects are around 600,000 miles compared to tens of millions of miles in the Oort Cloud. So if a spacecraft could successfully navigate the asteroid belt, it should, in theory, be able to traverse the Oort cloud from a density perspective. But the sheer speed of FTL travel introduces entirely new considerations. It raises an important point. No matter how advanced our propulsion, the Oort cloud reminds us that space, even in its vast emptiness, is never truly empty. It always presents unique, profound challenges for our exploration and expansion. It's truly a test of our technological and perhaps biological limits, forcing us to rethink our place in the cosmos.
What an incredible deep dive into the Oort cloud. From its mysterious, violent origins tied to the very birth of our solar system to its potential role as humanity's future frontier, it truly redefines our understanding of our solar system's true scale and dynamic nature.
It really does. So, just to recap briefly, the Oort cloud is our solar system's colossal, unobserved, icy shell. It's a relic of its formation, shaped by gravitational scattering from giant planets and dynamic interactions within the Sun's early stellar cluster. It serves as the wellspring for those long-period comets, acting as a fresh supply, and potentially harboring unique Manx comets containing pristine inner solar system material. While direct detection of Oort clouds around other stars remains beyond our current capabilities, theoretical models and the existence of those exocomet belts suggest such structures are likely common throughout the galaxy. The compelling evidence for Planet 9 highlights the possibility of a large undiscovered world lurking in its distant reaches, hinting at a more complex planetary census than we previously imagined. And looking ahead, this incredibly distant realm holds speculative potential as a vital resource for materials, a critical way station for interstellar travel, or even the ultimate home for future human civilizations adapted to life in the profound darkness between stars.
It's just a testament to the dynamic, ever-evolving nature of our universe, isn't it? And how much there still is to discover even in our own cosmic backyard, pushing the boundaries of what we thought possible within the sun's gravitational domain.
Absolutely. And maybe consider this. If the Oort cloud is not only that composite library of our solar system's past, containing chapters from other stellar histories, but also a potential haven for a hidden planet and a launch pad for future interstellar endeavors, then this invisible, icy frontier holds not just the keys to our origins, but perhaps the very trajectory of our species into the wider galaxy. What incredible stories might we uncover, and what new forms of civilization might emerge if we could finally journey out there and read those chapters firsthand?
A truly inspiring thought to leave us with. Thank you for joining us on this deep dive, and we encourage you, our listeners, to keep exploring the wonders of the cosmos. Until next time.